that would just about do it. Okay. Alright, I think we are just about good to go. So, we have here today another live stream for our math series on studying for the AP Calculus AB exam. So what I have here is that I will start with the 2013, now because last time we did the 2016. Well, this is the 2013 AP Calculus AB exam. And so we'll be going over the free response questions, and hopefully through that we should be able to then figure out next on what to do. Let me double check a few things here as well while I'm at it. Oh yeah, that's right, we need to change this. And so from there we should be fairly good to go to make sure that we are well on our way to be studying through this. Again, for anyone else that is going to be watching, you can always submit any of your questions through the chat and we should be able to try to answer that as best we can. Alright, so I think without any other further delay, we can go ahead and start with this. So, as before, I think this time though, if I can actually get that, that's what I kind of forgot. Just a minute here. I should have, this time with us, an actual graphing calculator that should be able to help us with the actual problem. So I think if you can see this here, let me run through a very quick integration. See, let's look at the screen here. So, if I were to do an actual integration there, yeah, that should be the function for integration. Let's go and use, and it's been a little while since I have been using this, but let's do something that's known already. So 5, let's go with x, if I can remember, 5x to the second power. And then I think for this kind of thing, it really is just going to be, let's go 1 to 2. I think that's the right syntax for this. Nope. Let me just make sure a couple of things here then from what I have to make sure I have the right syntax on the old classic TI-83. Let's see. Oh, it's variable first. Okay. So let's see if I can I switch this to insert mode here? Yes, I should be able to. We can insert in another x. Okay. Let's insert here another comma there. There you go. Okay. That's not correct. Let's insert right there another comma. There you go. Okay. Now that's a bit more like it. So we have here the full integration for 5x squared from the limits of 1 to 2, and there you go. Okay, yep, so that's how integration is going to work. We'll go through the steps to make sure we can show that every time we're going to do any integration on an actual graphing calculator. I believe there's some other models I might look into spreading out through. I know a lot of people like the TI-89 color. That's a nice blue one with pretty nice white background that people can use and see on. But for now, this is what I grew up with, powered by lovely AAAs that have not failed me ever since I took this class years ago. So we'll be going on with this, and we should try to hopefully see what it will look like once we can get everything going through. Good. So we'll leave this off to the side for now, and we shall go ahead and see what this next part is going to be. So we have the problems here. I'm actually going to, because of the way, unfortunately, that the quality of my printing paper, will be doing all the problems off to the side here instead of exactly on the paper itself. So we have 6 problems here that we're going to go through together, and so with that we should be going through fairly okay with some of the parts that we need. So I'll go start with problem number 1. Again, I'll write this down all on my actual notebook here that you'll be seeing. And then we should be well on our way to going through these problems. So as always, all the VODs will be on the YouTube channel itself. So anything else, we'll definitely can look through to make sure to see that. It will be there for any further review. So let's actually begin here. Start with problem number 1. So it says here that we are on, let me double check on this. So see, we have a workday rate here. So we have the function g of t is equal to 90 plus 45 times the cosine of t squared over 18. And then we go from 0 to 8 on the t interval. So, and it also says at t equals 0, we have 500 tons of the material of unprocessed gravel, and so we have a constant rate right here. It should be g prime of t, which is going to be 100 tons per hour. Okay, so with that, we're gonna have a rate at which we have the gravel being processed. We have the function right there. And so now the first question is very straightforward. It says just here find and g prime of 5. And then using correct units, interpret the answer in context of the problem. Okay, so we have something here about the way that this problem is going to do. Let's see. Let me make sure I actually make my handwriting as legible as I can for all of you to see. And if the camera could please focus. There you go. Okay, so we have this function here. We want to find g prime of t. So we're gonna have to go and do the work for that with our starting function here. So for us, g prime of t is gonna be equal to the derivative of 90 plus 45 times the cosine of t squared over 18. And we want all this to take the derivative in respect to time. Okay. So with that, we can run a simple derivative here. There's no need for a calculator on this right now. So this will be a negative 45 of sine, taking the derivative of cosine of t squared over 18. And then from here, we still have chain rule to apply. So we have to take the derivative of the inside of the sine function right there, which will be 2t over 18, which will then simplify to t over 9 if we want to make that side note over there. Okay, so with that, then we want to find g prime of 5. So once again, the original function g prime of t now from the derivative negative 45 times t over 9 of sine of t squared over 18. But this all then could be simplified one more time. The 9's can be removed on the denominator. So it'll be negative 5 times t times the sine of t squared over 18. Now if we want to plug in the 5, which they asked for, we're going to need negative 5 times a 5 times the sine of 5 squared over 18. Okay. Now here we can definitely put this into the calculator. So at least for one last thing to make our life as easier as we can, is that negative 25 will be the first coefficient multiplied by sine of 25 over 18. This should be very easily done in our calculator. So let me quickly put that up here. Okay. So again, it's going to be the negative 25 times the sine of 18 over 25. And just make sure our mode is going to be in degrees here. Not degrees, in radians, that's right, yeah. So confirm that we are in radians as shown in the blinking cursor right there. That we are in the radians, not in the degrees form. So we can get back to our problem of negative 25 times sine of 25 over 18, cannot make that mistake there. Let's make sure we do that properly. So it's 25 over 18 as shown in our line of work right there. So let's go ahead with that. And so from what we have here is that we're gonna result in a negative 24.58. 24.58. Okay. Let me double check on this for a second here. Yeah, I think we're still pretty okay on this for now. Yeah, because we're processing, we're gonna remove the amount of gravel from the plant, so it's gonna be negative 24.58 tons per hour, and that's removed. Okay, so it says here, although actually, it already this is gonna be in the GFT, which is already the rate. Yeah, so the GFT, this is already in the tons per hour. This is tons per hour squared. That's the rate change of gravel removed. So hopefully you can see that pretty okay here. Yep, so we have that much rate that is changed for the gravel that has been removed from the system. Good. So with that then, we can go ahead with that as one of our answers here. Okay. And so next up here, we have part B, which is requesting the total amount. Let's remove the calculator for now. We'll come back to that when we need it. Okay. So again, it's going to be the total amount, if our camera can focus here, the total amount of unprocessed let me make sure we're all good on that. Okay, so of unprocessed gravel that arrives at the plant during hours of operation. Okay, so if we're going to then describe the total amount of gravel that has arrived, again, keywords on that word total amount that arrives, we're going to need to take the integral here because we have GFT and that's our rate with respect to time. And that's the rate at which the gravel arrives. So if we want to find total amount, we need to find using the integral of that, and we would also need a definite integral such that we should be able to discover the actual amount that was used. So in terms of the definite integral, our definite limits here are going to be from 0 to 8. And so with that, we will be able to go and put together the function and figure out exactly the amount that has been added into this plant here. So by going from 0 to 8, again, we're taking a step back away from the rate of the amount that was added, but because of that, we get 0 to 8, 90 plus 45 times the cosine of t squared over 18. Again, the 0 to 8 was reflected from the time that the whole plant operates for the day, as t goes from 0 to 8. And so with that, if we take that respective time, we should be able to come up with an answer that will satisfy what we need. So this is where we're gonna have to go use, at least on this calculator, hit that math button for us to go all the way down to option number 9, I believe. Yep, the function integration, and then we put in that function. So it's gonna be 90 plus the all of 45 times the cosine of it's t squared, so we can use t if we want. If I can find that real quick. St, that should be t. Yep, so t squared over 18. Okay, so all of this though is going to be in terms of comma t, and then we're gonna go from the limits from 0 to 8 hours of operation. Okay, think for a second, and it comes out with 825.551. So we'll put that into our response here, 825.551, and that's gonna be total tons that arrived to the facility over the course of the 8 hours. Okay, again, it's just the starting minus the finishing. That's what an integral really does when you take the definite form of it. And so all that really means for us at that point is that we will then find out that there is a total amount of 825 tons that have arrived into the facility. So that seems pretty good for now. Let's go to part C. So is the total amount of unprocessed gravel at the plant increasing or decreasing at time of t equals 5 hours? So see, is the amount of gravel at the plant increasing or decreasing at t equals 5. Okay, and we need to show work for answer, which we already will be doing. Okay, so let's go and make sure we are knowing how to answer this type of question. So they're asking for the amount of unprocessed gravel that is increasing or decreasing at times equal to 5 hours here. Okay, and so with this, well, we just need to know about that rate in which the unprocessed gravel is arriving, because again, if we have the g of t rate, again, that's in tons per hour. Again, so we have two options here, right? If we plug in the number, if it's positive, again, that means gravel is being added, and then it's going to be increasing for us. And on the other half, we get a subtraction, which is going to be the gravel removed, which is a decreasing function instead. Okay, so let's have a look here then. Let's look at g of 5 is equal to 90 plus all of 45 times the cosine of t squared over 18. Okay, so I want to make sure we're looking at this properly on... Okay, yep. And then as well, right, there's also one more piece of information, is that this note here by the top of the 100 tons per hour, again, that is being processed, or in our case for this problem, being removed. That's at a constant rate in which they're removing that much gravel out of the facility. And so with that, we can go and take that note that we're going to compare this to the minus 100, the tons per hour that the plant itself is using up when processing all this gravel. So with that, let's have a look here. Now we can go ahead and start putting that through the system. So do the calculator. So it's 90 plus all of 45 times the cosine of, now it's going to be 5 squared up inside. Just a minute here. Sorry, it's going to be, and the calculator again, it's going to be cosine of, again, it's t squared over 18 as shown at the bottom there. So t squared over 18, that's going to be 25 over 18 in that cosine. And then we're going to have to subtract the 100 at the end of that for the 100 tons per hour that the plant uses. So we end up with negative 1.859 going to 3 decimals. So I'm going to write that down. So negative 1.859, that's tons per hour of the gravel that has been removed. And so because of that, that will definitely show through that we are removing or decreasing the amount of gravel in the facility. Okay, pretty nice. And we'll go to part D then, which is going to be, what is the maximum amount of unprocessed gravel at the plant during the hours of operation on this workday? Justify the answer. Okay, so let's take a note on the question. So I'll make sure we're making ourselves visible here. So they want to know the maximum amount of unprocessed gravel at the plant during hours of operation. Okay, so we have a few things to map out here if this is going to be the case, that we want to know a total maximum amount of material that is inside of the plant. So we have here for going from 0 to 8 hours, which is the total number of hours of operation. Okay, we need to keep track of the amount of gravel that is being added into the facility at a given rate, and then the amount that is taken away also in a given rate. So I think what might be helpful is that if we actually take a step here, if I take a step, we're going to graph it itself. Again, we can look at some local maximums for the function. Okay, and remember, right, we're looking at the rate function here as well. We're not looking at exactly the amount of gravel that's in the facility, but the rate function itself will be helpful for us to find out the local maximum for the actual plant itself. So what we can do here is that we can go to our graphing option here. So in our first graph, the y of 1, we can put in the 90 plus 45. Make sure I put this in parentheses. So 45 times the cosine of, make sure you have to change this to x now for graphing purposes, x squared over 18. Okay, and we need to subtract a consistent 100 from the graph because that's how much is being removed every time. So it's going to be a steady 100 rate that will be removed every moment. So let's make sure that we have our window here set, that our x minimum is going to go really just from -1, just so we have some spot there, all the way up to 10. And then for the scale of 1, y minimum needed 2.5 to positive 2.5, that should be fine. So I think we're all good here. So let's hit that graph button and let's see what we're looking at here. Okay, so our scale really does show us that we have reached going from, if you're reading this left to right, that we pass by the x-axis from positive to negative. So that is indeed a maximum, and then we go back up at the minimum later on, but that's not what we're worried about. We're worried about that maximum and our endpoints to see what the actual maximum amount of gravel could be. So again, we have 3 candidates. Let's figure out where that intersection is as well. So if we know the x value for that intersection, we can hit the trace, not the trace, the second trace, so that's calculation. We can calculate a 0. And let's see if we can get to, there you go, so left bound of that, left side of that dip there, and then we can go to the right side. Yep, so just one more to the right side of that bound, and we'll take a guess into it, and there we go. We end up with an x value of x equal to 4.9, make sure you see that, 4.9234. Okay, we can round that to 9235. So x equal to 4.9235. That's going to be one possible candidate. The other candidates, of course, is going to be the actual endpoints. So going to 0 and going to 8, we're going to now have to check the amounts of gravel that's in there. Okay, so the way that we're going to do that, though, is that for each of them, right? So at 0, that's pretty easy, because at 0, we already know exactly how much we have. They told us that at the start of the problem that our starting amount of gravel is 500 tons up there. So we can start with that as one of the candidates already known. Okay, and then we also actually do know the amount that arrives into the facility after all that time, which is 825.551. But that 825.551, that's the amount that arrived. But this is at the end of the day, so they ran for 8 hours. So we're going to take off 800 tons that have been processed. And then we're going to add back in 500 that we started with. Again, the 825 is just how much that came in throughout the workday, and it isn't exactly showing what the total amount that came in that they even had started with. So there's a little bit of difference there that we need to keep track of. But in any sense though, we have everything that we need to find our 8-hour shift here. So with just a little bit of simple addition subtraction, it's 525.551. That's how much we had at the end of the day. That's in the facility. And now we need the 4.9235. So that one's going to be a little bit different because this is now going to be a different integral of going from 0 to 4.9235. And then it's going to be that g of t. So it's going to be 90 plus 45 times the cosine of t squared over 18. And we still have to subtract the 100 from the rate because that's 100 tons every hour that's being removed. And so with that, we can then confirm how much is there from 0 to 4.2395. So if we go back to our original part here, and let me make sure, how can we go? Let me make sure I can get back to an older topic here. Is it just backing now? Well, I'll figure that a different time, but right now we're just going to have to redo the math function to get back to the integral again, the function integral operation there, so we can run another integral. So let's do the 90 plus all of 45 times the cosine of, this time it's going to be, we're taking an integral, so it's going to be of x squared over an 18. Okay, and all of that's still minus 100, and then we go for the variable of x, and then from the limits of 0 all the way to 4.9235 that we found before. Okay, there is something off with the argument. Let's have a look here. What would be the issue here? 1, 2, 3, 4, 1, 2, 3. Oh, I wonder if we don't have enough. I suppose we don't have enough, but we can just remove that set of parentheses. I think it will anger me for the... What is it now? I think we don't have enough parentheses then. Alright, let's insert another parentheses there. So I believe that does match everything up that we need. There you go. Okay, very good. Just some parentheses nonsense that I had to keep track of, but we have our actual answer there of 135.376. Okay, 135.376. But again, that's the pounds, not the pounds, that's the tons added. Let me make sure I move this over so you can see. Yep. So this is the amount of tons that are added, but we still need to keep on with the 500 tons that have been started with. Okay, and that 135 does take into account the amount of hours that have been removed, as that's part of the integral of 100 minus the 49235 hour mark of that maximum. So I think we're pretty good all on that. So let's move this over. So this ends up at the 635.376. Okay, so between our three candidates here that we can see so far, let's make sure that it's all in focus here, is that yes, between 0, 4.9, and 8, the 4.9 time mark is going to be the mark in which there is the most amount of gravel in the plant at the time. So let's take a note of that to finalize the answer. 4.9235 hours. That's exactly the time when we have the absolute maximum of gravel available to us in the plant. Alright, so that's it for problem number 1. I'll go to problem number 2. We'll do that, and then we should be able to return back to some answer checking to see how well we did here. So again, we have problem 2 in this packet here. I'll be writing down the problems as we go through, just for space-wise, and then it will be all reflected on the notebook that I have. Okay. So we have a particle. It says here a particle moves along a straight line for 0 for t up to 5. The velocity is given by -2 plus t squared plus 3t, all raised to the 6/5 power, minus t to the 3rd. Okay, and then the position is given by s of t. It also says it is known that s of 0 is equal to 10. Okay, and that's it for the context. Good. So we're dealing with a particle that's moving along a single dimension. We have its velocity function up there, and then we also have a starting position point. So again, position is s, velocity is v as function names. And so from this, we will be able to find now, here it says here that for problem number A, it says find all values of t in the interval t is between 2 and 4, for which the speed of the particle is 2. Okay. So the speed of the particle is 2. And now they used specific wording which you would need to keep track of. Okay. When we talk about speed, that is going to be in terms of a velocity equal to 2 or -2. The speed does not care for the direction. That's what velocity tells us, that it's the direction issue for this kind of problem. So with that, let's see what it looks like for either going to 2 or -2 on the part of this problem. Okay. So for v being positive 2, let's see, we can definitely go and tell that with this, I believe we might as well use, because we're only going from 0 to 5, we might as well use the graphing calculator here to determine that. Yeah, so what we can do here is that we can set up first equal to, so we want v of t is equal to a +2, which is -2 plus t squared plus 3t 6/5 power minus t cubed. So we can subtract this to both sides so that now we have a 0 function, which is easier to solve on a graph. So -4 plus t squared plus 3t 6/5 minus t cubed. Having in this form, and with 0 being on one side, is easier to find on a graph and easier for us to pinpoint. So let's go ahead and do that. Let's go into that function here. Yep. Okay, so it's -4 plus all over. Now we need to swap it to the variable of x for the sake of this graph. So x squared plus 3x, and all this raised to the 6/5 power. Okay, and we need to subtract it with an x raised to the 3rd power. Okay, so let's change our window here. Going from -1 all the way, we only need to go up to 5, so we'll go to 6. And we just need to see what it looks like in reference to the x-axis. Okay, so it looks like we only crossed twice on this side, so let's have a look. Let's go calculate some of the zeros that would best describe what's happening here. So where is, oh, there you go, we have that coming across. So our left bound is there, our right bound of that 0, give it a calculator time to calculate that, and we end up with a proper zero of 0.947. 9437, sorry, 0.9437 is one of the times we get. 37. Okay. Now let's go find that other zero that's on the other side. So let's go do a second zero analysis again. Let's skip on down. Let's see, make sure we're still where we need to be. Okay, there it is. So our left bound of the crossing the x is right there. The right bound of it is right there. So we'll take our guess here. And we end up with the x value of 3.1276. Okay. So those are still good for possible x values. Again, this is where v of that is equal to positive 2. But now we still need to go check for the negative 2 actually. So again, we want when v of t is equal to negative 2, that still matches a speed of positive 2. Because again, speed does not care about the direction, it just cares about the actual value of the number itself. So with that, we're gonna reform this function here that we started with, and we're gonna add 2 this time to either side. That's a plus, needs to be stuck in there. Okay, so from there, those actually cancel out. So 0 is equal to just t squared plus 3t to the 6/5 power minus t cubed. So here we should be able to find new zeros for the function. Let's just see if we can find out all of them. Okay, so back to the graph now. We just really need to just change a couple of things, one of which is that we delete that 4 plus, and everything else looks pretty good. We have the actual total function that we already have. So let's go and graph this, and let's see if we cross we need to. So we crossing at 0 is expected, but are we going to cross? We do cross one time, it looks like, for this. So let's go trace to find out where exactly that 0 is. So let's bring this around. It's coming around. There it is. Okay. So it's the left side. Let's go again on the right side. And let the calculator calculate that. Okay. We end up with a 0 of 3.4734. Okay. So 3.4734 is going to be another candidate. So it looks like we have 3 of them in total. So why don't we go note that down for now? That we found each of these that it's going to be positive 2 or negative 2. So we have 1, 2, and 3 different candidates for this function to be equal to positive 2 or negative 2. Okay, and all of them is in between the intervals from 2 to 4, and which one of them is not. So let's see if we can remove that. So this guy is no good because it's not within the interval. We almost got that wrong if you didn't pay attention to that. So we just have 2 possible times in which this can happen. Okay, that's the answer for part A. Let's move on to part B. It says here, write an explanation involving an integral that gives the solution s of t, and then they also use this expression to find the position of the particle at time t is equal to 5. Okay, so that is a little bit of a different scenario here, where now we need to figure out an actual s function using an integral. So it's not too bad for what we have here, but in either case though, we should be able to describe this out pretty okay, because if we then take the integral an indefinite integral, that is, of v of t in respect to time. That will give us the original position function plus some constant c. The only way we could know this constant c is that now we can use the s of t as one of the starting points, because we have the mark here s of 0 is equal to 10. So once we do find c, then we can quite easily plug for s of 5 to match exactly what they asked for at that start of the problem. Okay, so that's not too bad for what we have here. So why don't we go ahead and do that, because it looks like here we should be able to do this well, not entirely by hand here, but let's see here. Yeah, and so because this, if you want to find s of 5, I think we're going to have to go run definite integral, because yeah, this is not able to be done by hand. So we have the relationship here that v of t goes into s of t after taking the integral. So we have 2 points that we're looking for. We know one already, the time of 0 that was given to us at the start of the problem at s of 0 is equal to 10. So with that, we can come up to that at a later time. And of course, at 5 seconds, I'm assuming seconds here, it's actually going to be just about the same for that as well. So we can then plug in for v of t, which is the negative 2 plus t squared plus 3t raised to the 6/5 power minus t cubed dt. And remember, if we were to take this through the calculator, this is also will give us an expression that will be from the fundamental theorem of calculus, the s of 5 minus s of 0, the difference between the upper limit and the lower limit of the integral itself. Okay, pretty nice, because we do know s of 0 already as 10, and now this guy here, all of that can be then found by our calculator. So why don't we go ahead and do that? Okay, so let's go to our math button here and go to the 9th option. So again, we're doing our function integral. These are definite integrals that our calculator is allowed to do. So let's go plug this in. So negative 2 plus all of, we can call it t if we want to. So let's go to t squared plus 3 times t. Okay, and then because of that, all of this is raised to the 6/5 power, and then subtracted by t, that's not t, t to the 3rd power. Okay, and so all of this needs to be taken in respect to t, and our interval from 0 to 5 for this. So let the calculator think for a little bit as we run through this integration, and we'll see. End up at negative 19.207. Not too bad. It can be negative. Let's make sure we get 207, 19.207. Yeah. Okay. This is negative 19.207. That's the result of a subtraction of s of 5 minus s or s of 0, which was 10. Okay. So by that being subtracted by 10, we can add 10 to both sides. And so we end up with negative 9.207 as the position at the 5 seconds. Good. Looks like we tackled everything we needed to. We needed an integral expression, which is exactly what we gave them with this, that we put into the calculator. And then we actually ended up with the true position at the 5-second mark for the particle. Very good. Let's move forward to part C. Part C says find all the times of t on the interval 0 going for t going to 5. Is my thing here cooked already? I did not put my ink back into this pen when I should have. Okay, I'm gonna have to swap over to a different pen, which I think should be fine. It's actually a little bit thicker, I believe, so I think we should be all right if I use that. I think it should be still just as, oh well, yeah. Well, it's black ink now, but should be just as legible, if not even better, given that it's a thicker nib on this. See that fine? Oh, we can see that just perfect. Good. Okay, so 0 for t going to 5. Got to make sure to fill that pen up. That is one of my favorite pens that I do like to use for math. So for this, we're going to take this down as a note here. That we have that interval, but thing is all the times at which the particle changes direction. Okay, and then justify the answer. Okay, good. Oh, that looks pretty nice against that black paper, the white paper on the notebook. Good. So we want a change of direction. Well, that just means that we have to look at the v of t graph now, wouldn't we? Because we need to find, again, where we cross, if the graph has any changes like this. Again, we're looking for the crossing of the x-axis. And that will help us determine if that particle has changed direction. So, going back to our function, we don't have everything exactly in line because we did some manipulation of the function. Notably, of course, is that we need, if we're going to insert this in, actually it doesn't have to even be inserted, no, we just go to the very end here, that we just need to do -2 at the end of that. And this is the proper reflection of the function that was given to us at the start of the problem. Make sure our window is good. We're going from 1 to 6. That's perfectly fine. So you got 1 there, 2 there. Looks like only 2. All right, good. So we only have 2 ways in which this crossed the x-axis after time of 0. And so, because of that, we're going to find those times in which they crossed, and that for us is a change in direction for the particle. So, let's go trace in another 0. And let's bring this all the way back to the first bound. Make sure we get close. There you go. So left bound of that curve. Oh, nope. Let's not do that. Let's try that again. I actually hit the wrong button. Yeah, that's where it should be. There's 0.4, and then let's go right of that, and let's have the calculator figure that out for us. We end up with a 0 of 0.5260. Okay. 0.5260 is one of the t's, and let's find the next one. So let's go trace in another 0. Let's skip ahead here. Closer here. There you go. So left side of it, so right there. And let's make sure we're on the right side of that right there. And let's have the calculator figure that out. And we do end up with another close to 0, 3.3178 if we gather that. Okay. 3.317. Okay. 3178. That's the other time in which we actually crossed the axis. Okay. Pretty good. So let's go ahead and make sure that all of this is all together here. And so we have here just the time, a lot of times which change directions with these two. Yep. So let's make sure we secure that again. And at least for us, if we want a true justification, our answer here will be that the particle changes the sign of velocity at the given times, signifying a direction change. All right, not too bad for something to start out with over there. Okay, so we have that pretty good. So let's go to the last part of this one. It says here, is the speed of the particle increasing or decreasing at time is equal to 4. And give a reason. And here we go again with the whole issue of speed inside of these problems, right? Because speed is just that relationship of velocity and acceleration. I know it's often thought that speed is just simply velocity, but that's not the case. Speed is going to be a comparison between velocity and acceleration. We need both to truly understand what the speed is for any given object that's moving. So because of that, we really have 3 options here, right? Okay. 3 options because, well, really only 2. Let's change to 2 to make things simpler. Okay, so again, either for these kind of problems, it can be speed up or speed down. I know we often would say slow down in our English language, but just to keep everything consistent, it's going to be speed up or speed down. Speed up is going to be the relationship if velocity and acceleration are greater than 0, and speed down, not greater, sorry. Let's change that. So velocity is going to be, so 0 or acceleration is greater than 0, or if velocity is less than 0 and acceleration is less than 0. Like I said, it's a relationship between the two, which means that you will compare both of them to each other and see if they're both the same sign, or it will be considered speed down if velocity is greater than 0 and then acceleration is less than 0, or velocity is less than 0 and acceleration is greater than 0. So again, same sign or different sign, that's what you're looking for, right? Because if they're both negative, that velocity number will get much larger negative. But because it's speed, it does not care about the sign. And of course, in the opposite way is that if velocity and acceleration are both positive, that velocity number is going to keep going up, meaning that the particle is speeding up, right? So that's why it's that constant look at the relationship between both velocity and acceleration. So that obviously begs the question that we must then see what the acceleration function looks like for this particle. So a of t is going to be noted as v prime of t. Okay, and so the thing is, we only need to care about it at the moment of 4. Oh, so we could do this by hand, which I think should be fine for us to do. But for many people with graphic calculator, do we have? Let me double check. Do we have a form that does derivatives for us? Yes, it does. Okay. Let me double check here. Make sure I'm. Let's see. I'm on the right track. I want to make sure I'm on the right track here. At least with the. Yeah. Okay. So the syntax can be just about the same. Okay. Good. Alright, good old Texas Instruments coming in clutch for us like that. So yes, we're just going to type in the function now of the thing we want to take a derivative of. It will do that, and we let it know which variable and which number we want to plug in for. Again, this function only gives us an actual number, so it only works for the case like this, where we are plugging a number like t is equal to 4 into a derivative. So we can go ahead and do that. So with our derivative here, it's negative 2 plus all of t squared plus 3 times t. Okay, and then with that, all of that is raised to the 6/5 power, and then we subtract it with t raised to the 3rd power. And with that, we are only going to take this in respect to t, and then with the actual value of 4. And it does give us an answer. This does give us an answer of negative 22.296 if you go to 2 decimal places. Okay. So acceleration of 4 is negative 22.296, and this is gonna be. They don't tell us anything about the unit, so we just leave that as that. Okay. Now the velocity of 4. Did they let us know No, we only got the... We don't have velocity of 4. Okay. So, looks like we actually need to plug that in, though. That's pretty simple. So, it's negative 2 plus 4 squared plus 3 with the 4 plugged in. 6/5 power minus 4 to the third. Now, this one will definitely be done on the calculator here. Not to be confused with the YouTube short that I made about some very simple arithmetic being used on the calculator. Always remember to keep up with all those shorts. Those are really fun to make, so I hope you guys really do enjoy that. But nonetheless, let's go back here for a second here. Is that we're doing negative 2 adding with 4 squared plus 3 times 4. That should be an easy 12 to plug in for us. But all of that is raised to the 6/5 power. And then minus a 4 raised to the third power. So by plugging in for this velocity function, we had negative 11.476. Okay, negative 11.476. So we have the acceleration and we have a velocity that we're keeping track of here. And when you look at that, they are both have negative signs on both of them. So with that, we can then conclude that this particle is speeding up. And why is that? Again, because both acceleration at 5 is less than 0 and less than, not greater than, less than 0, and the velocity of 5 is also less than 0. Okay. And there you have it. Looks like we have, let me make sure we box our answer here for this. Okay. We've answered the first two problems that are the calculator-based problems. I can now toss this to the side here because the rest of the problems on this packet, which we still have 4 more to do, are all non-calculator problems. But with what we have here, let me go ahead and swap over to, make sure we clear this out to do everything here properly. Let's clear this out on all the stuff here so we can switch over to our main monitor here and take a look at what we have here. So again, this is the answer key to it. Again, I'm doing all the problems live, so we'll be looking at this until we're actually going to be in the correcting part. But this is not it. Just a second here. Let's go back because this is the actual problems themselves. I need to hurry up and make sure I show the actual answers. Just please bear with me for a second here. There we go. The scoring guideline. Let's go back. That is more like it. Okay, very good. So we have the scoring guidelines here of what we have. So now we have, yes, the actual answer. So let's go look at this one at a time. I'll mark this through. And then from there, we should be going along fine. So I'll take any notes on our notebooks and I'll definitely go back if there's anything we need to go over with again. So going back to problem number 1, I got negative 24588. That's good. And then they want the interpretation of the units. So the rate at which gravel is arriving is decreasing, yes. So they want a change in the rate at which the gravel is arriving. That was the question to part A. So I got this correct. So actually, let me also show you as well what this looks like, at least for what I'm going to do here, is that I'm marking this problem 1A. So from problem 1 up there, problem 1A is marked as correct for this. And we also check in the next part, which is the reason that it's the change in rate of the gravel in the yard. Okay, so that is indeed going to be full points, 2 out of 2 for me. I like to see that. Then let's go over to part B. Okay, it says here that it's 825551 tons, the integral and the answer. So the integral, that's a check for 1 point up there. And of course the answer is correct as well. So that's a fully correct part with both points going 2 for 2 on that. Okay, and then part C here is that we're looking to see if unprocessed gravel is increasing or decreasing. So we are decreasing, and then we need to compare it to that 100, which we just did. We have that minus 100 that we are comparing it to. So we are less than the amount, right? The amount that came into the plant was less than the amount that was removed from the plant, right? So again, it's kind of like the 2 different levels that we're looking at here. So because of that, this is indeed one part that is correct for the first point, comparing between the 2 rates. And then our conclusion now, of course, is that there's more being removed at the time at 5 hours. So that's another 2 for 2. Got this correct here. Very nice. All right, and lastly, part D here is looking at, we want a prime of t, okay, which they guess the total amount, but I didn't really write it as the function a because they didn't ask us to do that. But still, the setup is going to be just about the same here. Us actually keeping that minus 100, that's actually part of what they wanted us to show if we wanted to find the total amount. And so for the 3 different considerations for a of t of 500, 635,376, and the 525551, again, all those did line up exactly for the 3 candidates that I was looking for. Even that 4.9235, that value right there that I was eyeing, and we figured out from the calculator as one of the possible local maximums that we can solve for. Okay, so did they ask us for the actual amount? Okay, they did want to know the maximum. We do have it on there, I just didn't exactly write it down as one of the answers. That's why reading the question is so very important. The answer is buried in there. It looks like we just didn't really show that. But the time though, we definitely do have. Answer, justification, they're all good. So we are consider this correct at 3 out of 3. So to see how many points was out of, so 4 of them. So 2, 2, 2, so that's 6, and another 3 makes this a total 9 out of 9. And that's a heck yeah point right there for us to really enjoy, because we got that all through and through correct. Very good. So be onwards to problem 2, and that we'll be looking at here, of that particle that's moving. So let's have a look here. We have the actual speed of the particle here. So by looking at that, at least a speed particle of 2, we want the different times for that. So 1276, and then 3473. Yep, both of these are good value times. Consider the fact that we are doing both positive and negative 2. That's another pointer in which they wanted us to look at. If our camera can focus here. Okay. So that's what they want us to focus on, is to make sure that we were both considering positive and negative 2 on the velocity, because we're not looking for velocity, we're looking for speed of 2. And so we have to go consider both positive 2 and negative 2 on the velocity function. So looks like I got this correct for 2 out of 2 on that one. And then next up we have on part B, we need the explanation, and then we need the proper solution for the particle at the position of the particle at time of 5. Okay, so it looks like we got this down correctly with how to do the definite integral for the velocity function, and then with us separating out the 10 from the starting position. Looks like that is all good. That's exactly what I want to see. And of course, S of 5 being negative 9.207, that is good as well. So we're still 2 for 2 on this one as well, and this is correct. Very nice. Okay, onwards to part C here. So they want us to know all the times in which the particle changes direction. Okay, so when v of t is equal to 0, again, now that I did show a little bit on the graph part, again, now it's a change of sign. Again, that's what we're looking for with the change of direction. So 5260, that's a little bit off, but I think we should be okay. And then 3178, that's very good. Yeah, I think both of these should still be very good for within the margin of error. That's something to note with these kinds of calculator problems, is that either the graders will look to see if one or the other. Again, close enough is usually the main idea here, and the justification is really actually 2 parts of this problem. So the justification really counts as 2 points, considering that's how we're using to even solve this in the first place. But in what way I'm going to grade myself, that's still considered 3 out of 3. So that is a correct section as well. Yeah, the decimals will become a lot more stringent in the non-calculator part. But in the calculator part, I think they should still give me full points on this. Just about everything else is where it needs to be. Okay, lastly, we'll have part D here, where we're looking at the speed increase or decrease on this. Our velocity is the negative That is correct, negative 11, and acceleration is negative 22. So those are good. Those necessarily weren't points actually in the problem, but they do show it as part of the work that was needed to lead to the answer. But of course, the conclusion though is that because they are both negative, the acceleration and the velocity, that is enough to let us know that we have the right answer. So we're 2 for 2 on that. Okay, so the same number of points is going to be, let me make sure that we write down this correct. So the same number of points is allotted to this question as well. So I can start with part A. A is 2, 4, 7, and then 9, right? 9 total points. 9 out of 9. Again, that's a yeah for us. So it looks like we got 18 out of 18 points that we could have gotten for the first two problems, which are all the problems that will include a calculator for this exam. I'd say we're looking pretty sharp on this, and so I think we'll be ready to move on to the next section on answering problems. Okay. Let's make sure we're doing this properly. Okay. So let's go ahead and move on to question number 3. So again, I have the packet here physically, just as a reminder. I'll just be copying down all the important information over to the notebook because there's not enough real screen space to show both at the same time, at least for this. Okay, so with this, I will be copying over the actual table itself of this section here. So we have t in minutes, and then c of t. Okay. I'm gonna make sure this is problem number 3. Okay. Let me just make sure I change a little something here. Okay. All right. Very good. Then I think with that, we should be good to keep moving forward. What we have here is that, let's see here, that our time is a table that goes from 0 all the way up to 6. So 1, 2, 3, 4, 5, and 6. Okay. Make sure we can see all of that. And then we have our C of T in ounces of 0, 5.3, 8.8, 11.2, 12.8, 13.8, and 14.5. Okay, so we have hot water going through a coffee maker, and so the amount of coffee goes from, again, T is going from 0 to 6. Okay, and then T is in minutes. Okay, and so yeah, we just have that really table there. Okay, so it says here to use the table to approximate C prime of 3.5. Okay, and then indicate units of measure as well. Okay, so this is pretty nice because we can go ahead and use a little bit of, hello, why camera, hello, please. All right, so we can go ahead and use the mean value theorem for us to estimate, again, to get a good idea as to what a possible derivative looks like. So given that it's 3.5 that we want to look for, we're going to be taking the slope, so basically an m here, or the change, right? The delta t, or c, sorry, y over x over delta t. And we're going to use it between 3 and 4, right? Because the in-between mark for 3 and 4 for us is going to be basically 3.5, where we need to be for this kind of problem. So let's do y2 minus y1, 12.8 minus 11.2, over x2 minus x1. So again, average rate of change between the 2 points at 3 and 4. If we really wanted to show this, again, this is implying that we're doing c of 4 minus c of 3, and then again, the time at 4 and then time at 3 in that subtraction. Okay, so with that line of work, we should be able to come up to a pretty easy fraction here. Looks like it should be 1.6 on the top and 1 on the bottom. So 1.6 is going to be the result of that. And they did ask us for the units. So if C is measured in ounces, again, that's going to be the ounces per minute that the coffee is made. Okay, not too bad. Looks pretty good enough to me. That we explained ourselves as to what we're looking for by understanding what average rate of change looks like as an approximation for a specific derivative. Okay, part B. They're asking, is there a time of t that it's in between 2 and 4 at which c prime of t is equal to 2. Okay. So now we need to understand this. We have something here that we want to know, at least for a mean value theorem. Again, we want an MVT business going on here for us to know about where this thing is headed. Okay? So there's a couple of things that we should notice already, is that if we want between 2 and 4, right, we're going to have to go check to see, again, this is the mean value theorem, right, is that we are trying to guarantee. Okay, so sadly, again, a word that is often thrown around too lightly, but thankfully in mathematics, there are plenty of times in which we can guarantee certain values. Okay, and in our case, that will be done through MVT right here, the mean value theorem. So because they gave us a time interval from t of 2 to 4, we will do the same thing of looking at the average rate of change for 2 and 4. So that's going to be c of 4 minus c of 2 and time at 4 and then time at 2. And the whole purpose of that is to know that, again, if the average rate of change matches one of our derivatives, it's guaranteed that it's going to have that derivative at least at any single time point. So for us, we can go ahead and do 12.8 minus 8.8 all over 4 minus 2. That gives us a 4 in the numerator and a 2 in the denominator. That does end up with 2 as the result of the average rate of change. So again, the average rate of change does match the c prime of t all at 2. And so those are the conditions for mean value theorem to work. That for this, we are guaranteed that yes, right, there is a time when we go between time of 2 and 4 that c prime of t is equal to 2. Now, do we know that time? No, we don't. We don't have enough information in order for us to decipher that. But mean value theorem at least guarantees, again, that word, it guarantees that one does exist. We simply just do not have the information to find out all of it. Pretty nice for us, so we can go box that as an answer for ourselves here. Okay, so onwards to part C. Okay, it says here that we will use a midpoint sum with 3 subintervals of equal length. Okay, from the table, let's make that note as well, from the table. Okay, to approximate, oh, now we got this. We got a great doozy. 1/6 of the integral from 0 to 6 of c of t dt. Okay, and then using correct units, explain the meaning of that 1/6 0 to 6 c of t dt in the context of the problem. Alright, pretty nice. We've got ourselves a little bit of a wacky problem, but it should be something that we have gone over before, that there should be no problem for us solving for now. Okay, we have this integral right here. Okay, but we also actually want to look at a 3 subinterval of midpoint sum. Okay, so that's quite a bit of an interesting prospect for us to have, but nonetheless, though, it should be pretty easy for us to follow through with. So, with our 3 subintervals here, we can then see to it that we have ourselves some work cut out for us. Remember our midpoint here, the midpoint sum. Again, we're going right in between each level of the y values that we're looking for. So in order to do that, we have our table here with 3 subintervals, and we have 6 points. That means, again, we have 3 rectangles that we're going to take the areas underneath for, but of course at which moments, right? So with 6 points, again, we have, with 3 rectangles, we're going to 0 to 2, and then 2 to 4, and then 4 to 6. Again, these are going to be the t values. Again, the t values for all of those guys. Okay, and thankfully we don't have to do any sort of guessing here, because the midpoints, each of them are going to be 1, 3, and 5, right? Those are the t values in which we can find the heights, the c of t, right? For each of them, 1 is going to be 1 comma 5.3, 3 is 8.8, oh no, sorry, 3 is 11.2, wrote that wrong. 5 is 13.8. So we have now the actual corresponding heights to each of those rectangles. Now, of course, how big are the rectangles? Each rectangle obviously needs a base and a height. We knocked down the heights for each of those 3 rectangles. Now, what about the base? Well, thank goodness is that the base, though, we already know that we've already written them out with 3 subintervals of 6 points. That means the base needs to be equally 2 across each of them. So it looks like we have everything set up here with 3 different heights, all of the same bases here. So we can do good old distributive property here, that the area underneath the curve for us is 2 multiplied now across all of the bases. So each of the bases now is going to be, right, 2, which we can factor out and multiply later. And then we need to add up each of the heights that we're referring to for this problem. So the heights of the first one is 5.3, second height is 11.2, third height is 13.8. Okay, so unfortunately though, that there is no real issue that we can't really take our calculators with us. If only though, we can hold on for just 1 second here, is that we can get something better than a calculator, if I can find it. Yes. My own personal calculator, which I can go and show for today, right here, is my glorious abacus here. Quite big. I should have brought one of my smaller ones, but this should be good enough for us to use to solve for that area. So I can do this entire summation using this nice little red bead as a decimal point for us. Okay, and so with that, we should be able to go along with going with 5.3, and then we want to add an 11, 11.2, and then a 13, that's exactly there, 0.8. So we go to 3, and then we just add 1 there. Okay, so 30.3 looks like is going to be the total amount. That looks pretty okay. 30.3, you multiply by that 2. And so multiplying by 2 just gives me a 6 on either of them. So it's 60.6 as the total area. Okay, so I believe I should be finding more excuses to use this, hopefully, in my live streams, if I do hope I could. But in either case, I think I should be able to see this more often in any future videos. Again, I think this is one of the greatest inventions for people to actually do math by hand instead of having to rely on these fancy calculators, which quite honestly shows in the short that I made that it just wastes a lot of people's times. But nonetheless, the good old abacus will be back on our side soon enough. So let's go back to it though. That with this situation that we have, that the total area underneath the curve that we approximated is 60.6. Okay, now the main issue though is that we have a problem with it now, because they don't ask us for just the area. They wanted to know the total actual I guess the problem here, if I want to write as such. That problem is the 1/6 from 0 to 6 CFT dt. This came out with our approximation, right? The integral from 0 to 6 with those rectangles at the 3 subintervals at 60.6. And now we need to go by 1/6 of that. Okay? Now, thank goodness that they chose some very nice fractions for us, because this works out to just being 10.1. Now, of course, what are the units, though, of all this, right? What did we just do? What does taking an integral and dividing it by, right, the actual limits, what does that do? If only we could remember exactly what that is. Of course, that's going to be, this is known as the average value. Okay? Think about this, right? Because if an integral here, right, if this guy, the 60.6, is noted as the area under the curve, right, and again, we have the total expanse of all that we have across the total function, but then we are dividing it, right? We split it up into all the individual points that we came across, right? From 0 to 6, that full expanse all the way across. Again, we took the full area, and then we cut it down to the individual parts. Well, that should be an average value of the y values themselves, because we got rid of the entire x part of it instead. Again, by making one value, dividing it all, we are getting an average across the board. So if that's average value of what, right? It's average value of the C of t that they asked us first at the start of the problem. How convenient. C of t, if that's the ounces that of coffee that was made, well, that just goes to show that what we found here was the average ounces of coffee made between 0 to 6 minutes. So that's what we ended up with as the main portion here for this problem. Quite a few steps, but I think we're all the better for it. Okay, and then lastly, let's go to part D here. So they're asking in part D for us to find the amount of coffee actually, let me still check here. Not the coffee, the coffee in the cup. That's what I get reminded, because the table that they started with was that's the actual amounts that were in the cup at any given time. That's the average amount of coffee that was in the cup across the entire 6 minutes. So the amount of coffee in the cup is modeled by B of t is equal to 16 minus 16 e raised to negative 0.4 t. Okay, so using this model, okay, it says here find the rate at which the amount of coffee in the cup is changing when t is equal to 5. Okay, so we want to do the change there. So of course that just means we need to find here b prime of 5. Well, of course in our case means that we need to first find b prime of t, and thankfully this guy is actually not too hard to find by hand. So if we want to go 16 minus 16 of e raised to the negative 0.4 power times t, and we want to take the derivative respect to t for all of that, it's not too bad, because 16 will just go to 0. This guy will have to experience a little bit of chain rule for us, but it shouldn't be too hard with the negative 16 e raised to the negative 0.4 t. That all of that stays exactly the same. We just need a new coefficient of a negative 0.4 coming out for us. Okay, not terrible at all. So we end up with the negatives will cancel out, so we'll end up with a positive 16 times 0.4. Well, if we knew a little bit of our math here, that will literally just turn into a 6.4, and then e raised still to the negative 0.4 t. Okay, and then now if we want to go b, because this guy here is b prime of t, if we want to go b prime of 5, that's going to be 6.4 e raised to the negative 2. Negative 2. is 5 times 5 times 0.4, yeah. So it's -2. Okay. And then we just quite simply leave it like that. And that's the ounces per minute by keeping up with the rate units there. And because this is a non-calculated section, we can leave it like that. Believe it or not, that is the exact solution, right? With e being an irrational number that does not have any end to the decimal point, we just leave it as e, and that's exactly what it is, because we all understand what e is. It's just that we're not going to go into the depths about what the numbers themselves are. That's just the value that we've assigned for it. Okay, and that should be problem number 3. Not too bad, if I do say so myself. So now, let's flip this over, and we'll have a look at problem number 4 here. So problem number 4, we do have this guy here, a nice big graph, according to this. How very nice of them to give us the actual areas underneath each of those curves. I wouldn't mind that. But let's go across this now, just to see what we're dealing with. And as always, I'll be copying over all of the questions in the problem here on my notebook. So this is problem number 4. Okay, so we show the graph. This is a graph of f prime. Okay, so I think I can go about making this here. We got the time here, 4 and 5 on top, 2 on the bottom. Okay. Keep with the tick mark on 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. 1, 2. Okay. So let's see here. At 1, 0, we have 1 point right there, and then at 3, 4, one there, and then 1, 2, 3, 4, 4, 0, we got 1 there. And then 5, -2, and then 6, 0, and then 8, +5. Good. Okay. So I got our points here, and we're going to start at 0, is that 6? 1, 2, 3, 4, 5, 6. Yeah, 0, 6 we're going to start at. Okay. So our curve looks something like this. A little bit sharp for my taste, but I think we should be all the better for it. There we go. Okay, so we have this guy is the area of 2. This is the area of 6 up there, area of 3 between there. Okay, and then the area of 7 over there. Okay, so we got them all marked. We can refer back to that in our future problems here, but we still have the rest of the context I think I should write up here. So this is twice differentiable. Okay. And then we go from 0 to 8. Yep. So 0x going up to 8. Okay. So we have the horizontal tangent lines at x is equal to 1, x equal to 3, and x is equal to 5. Okay. And then the areas are shown. Yep. Okay. And then we have 1 point here. F of 8 is equal to 4. Okay. I think that might be helpful for us at a future time. But other than that, that's all the context they're willing to give us. I can do the points here as well. This is 1, 0, 6, 0, 6. And then this is 3, 4 up there. Then this is 5, -2. 4, 0 over there. This is 6, 0 over there, and then 8, 5. Okay, there you go. Very good. I think that's all that we need at this time. So we can move on to problem A. It says here for us to find all the values of x on the open interval 0 to x to 8, for which f has a local minimum. And then justify your answer. Okay. Pretty nice. So, what can we do about this? Right. Well, I think for what we have here is that we want to find local minimums for this guy. And always remember that we have the f prime graph, not the regular f graph. So with the local minimum, we need to know for the f prime again, we need to go crossing between a negative to a positive side just on the graph itself. And that would mean that it's a local minimum for the function. So let's see here. Crossing from negative to positive, we really have only one possible point, which is that one, the 6, 0. Again, at the 1, 0, it just touches the axis and it leaves. And then this one going from positive to negative, that's not minimum, that's maximum. Okay? So we'll say here f has a local minimum at x is equal to 6. Our justification now is that the f prime graph changes its sign at x equal to 6 from negative to positive, signifying a local minimum. Pretty straightforward for what we have right there. Pretty nice. So we can keep along with that momentum there, and we can leave this essay of an answer back here just for the time being, because otherwise they haven't really asked us for anything else for this first problem. So let's go ahead and move forward with part B for this problem. Okay. So it says here, again, if we're going to make sure that we're showing this again, is that we're doing still the 2013 AP Calculus free response questions. But with part B, I'm gonna read that down and copy it over to the notebook, as I don't really have too much space for this camera as of right now. So part B is asking for us to determine the absolute minimum of f on that closed interval 0 to 8. Okay, an absolute minimum problem. That's pretty interesting to keep up with, because absolute minimums means that we're going to have to go through a whole list of candidates. So we have the endpoints. Those are always a valid option to look at for minimums, simply because of where the graph starts at. That could be just the lowest point to begin with. So our endpoints are going to be, of course, x is equal to 0 and x is equal to 8, given what the graph starts and ends at. As you can see, starts at 0, ends at 8. Those are two possible candidates we're going to have to go look for. And then we're also going to need to know the next local minimum here. We're going to compare that as well. Our local minimum then is going to be where we cross from the positive side down to the negative side for the derivative graph, which is exactly what they gave us from the start. Going from the positive to negative side, that is going to be right there at that point, because we're going to be crossing the positive y values into the negative, signifying that the slope goes from positive to negative, meaning that we have a local maximum. Okay? So because of that, we're going to go from having this point here at x is equal to 4. So we have these three as our potential candidates for this type of problem. Okay, pretty nice. And so, right, we need to go and see if we can figure this out. So thankfully, we already know x of 8. So f of 8 they've already given to us as 4. We can hold on to that for our comparison afterwards. But then we need to know x of 0 and x of 4. Okay, so now we're gonna have to go and figure this out. So we have now integrals that we can use, because they did give us parts of the areas for each of this graph, which is very helpful to us because we'll be using that in the integral part. Because again, integrals are just simply the areas underneath the curve. So for us, if we want to take the integral of this graph from 0 to 8, our fundamental theorem of calculus will still hold, is that we're dealing with the points f of 8 minus f of 0. Again, that's going to be equal to that total area between those 2 points. And because we're looking for just f of 0, we can do some simple algebraic moving along here. And so the area can be tossed back. So again, if we have f of 8 minus the area, and that's equal to f of 0, we have everything that we need, because we do know f of 8, we do know the area, we do know both of these guys. Area we can easily calculate, leaving f of 0 on its own. So f of 8 being 4, subtract that from the area. Our total area ranging all the way from 0 all the way to 8 as we move along. We're going to have to take a look at each of those guys as we go along. So our first area is a positive 2. Adding that with the positive 6 for the next section of area that we're looking at. And then we have down here an area of 3 that's underneath the curve. That is negative area. I don't know why I got rid of the ended the parentheses, so we're not done yet. So minus 3. And then our last bit of area back on top, reaching up to 8, is a positive 7. Okay? So as we 4 minus, we have all this as 2 plus 6 minus 3 plus 7. Some very simple math here. That will go to 8 minus 3 is 5, adding a 7 is 12. So 4 minus 12, that's going to be a negative 8 total. So this is going to be the next candidate, f of 0, with a negative 8. Not too bad for something that is a little bit lower than our first starting point. But with that, we should be good to go and see what the next part is going to be like. So we can go then with our last candidate here of f of 4. And again, we're still using our fundamental theorem of calculus in order to figure that one out. So that's going to be f of 4 minus f of 0. Now, thankfully, we already know what f of 0 is. We just found that out. So we can put this together to make it look like according as the following. That's the area. So f of 4 is equal to that same area now added with f of 0. Okay, so the area up to f of 4 now, if we go back here, the area includes the first part of area of 2 and the second part area of 6, and it ends right there at the 4 that we circled. So that's good. So the area that we're dealing with is a positive 2 and a 6, and then we're adding that with a negative 8 from prior. That's going to be a positive 8 minus an 8, which is 0. So f of 4 is equal to 0. So between these three candidates that we're dealing with up here of the possible max absolute minimum, well, that leaves us with f of 0 being the absolute minimum. Okay, our work speaks for itself, at least for all the things that we needed to do to make this a reality. And so with that, I think we're good to move on to the next section. Okay, so we did all the work needed for the absolute minimum. Again, if you want to go over this really quickly, is that we're using fundamental theorem of calculus to figure out what these definite integrals are, which again is going to be the difference between the 2 points in which the integral started from. We knew what f of 8 was because they told us in the start, and we can work our way to finding what the rest of those guys are because of it. Okay, very good. So part C is asking for on what intervals contained in 0 to 8 for x is the graph of f both concave down and increasing. Okay, a really good problem for us, at least in the sense for it being something that we want to talk a bit more about for our thought process for the main parts of why we do this. Okay, so the vocabulary words here for us is that it's both concave down and increasing. That's what we're looking for, right? What those means for us, right, of course, with concave down, meaning that the second derivative is less than 0. Again, that's our conclusion to understanding that's concave down. Okay, and increasing, meaning that we have f prime of x is greater than 0. Okay, So with this, we're going to need to do a little bit more analysis behind that graph that we started with for us to understand. So for us having the first derivative greater than 0, that should be pretty simple. Because if it's going to be increasing, we just need to know, right, that the first derivative graph, the one that they gave us, simply has to be above 0. And we have quite a few sections to do that for us, right? We're going from 0 to 1. Again, we can't include 1 because 1 stops at 0. That means that it's not increasing at that point. So 0 to 1, 1 to 3, and then 3 all the way to 4. So it goes 0 to 1, 1 to 4. We skip all the part that's underneath, and lastly 6 to 8. Okay? So let's make sure we have that down correctly. So at 1, we need to stop, and then at 4, we stop again, and then at 6, we stop again. Okay? So from 0 to 1, as you observed, that is increasing because it's greater than the axis from going from 0 to 1. And then from 1 to 4, again, this entire function area of the function now, all above the axis. So that was also going to be increasing. 4 to 6, though, this section is underneath the curve. And so that's going to be a negative there. And then 6 onwards to 8 is all going to be increasing again because we are above the axis at that point. So we have a lot of sections back here that we finally made notes on that the original function f is indeed increasing. Okay, but now the question, of course, now is next about concave down. How to know anything about concave down? Well, if the second derivative is less than 0 and we have a graph of the first derivative, all we need to know is that, we need to know where the f prime is then decreasing. Right? That is our note that's going to save us here because that will decide as to what's happening with the second derivative. Because if it's the first derivative that's increasing, decreasing, that will give us positive, negative values on the second derivative. That relationship between how to get from first all the way to second derivative is really important for us to remember at this time. So where is that function f prime decreasing? Well, looks like we got one spot here from going from 0 to 1. That's a whole slide downwards on towards 0. Then we have another section going from 3 all the way down to 5. Notice we did cross, but the entirety in which this guy is decreasing all the way stops at 5. Everything else is increasing, so we really have 2 parts here. Okay, going from 0 to 1, again, that's a decrease. Going from 1 all the way up to 3, that was an increase. But then 3 going all the way down to 5, that's a decrease. And then 5 all the way up to 8, that's an increase. So our analysis looks something like this, with 2 decreases from 0 to 1 and 3 to 5, and then for the first derivative. Okay, so remember they are asking us for both. We want both the increase and the concave down for this graph. Right, so we must satisfy both to put them into any part of our interval for us. So to begin with, of course, is that the 0 to 1, that interval is definitely good with a negative on the first derivative, but a positive, positive on the first derivative, negative on the second derivative. Okay, then we only go from 3 to 5. That's the next section, and 3 to 5 is all encompassed inside of, well, not entirely, sorry. So 4 to 6 is encompassed inside of the first derivative, but that's negative, so none of those work. But we do have a section going from 3 to 4, which is encompassed in a positive section for the first derivative. So that will be the next interval. So we're going to union that with 3 to 4 as the next interval. And those will be the only 2 intervals, at least, for which the first derivative is positive and the second derivative is negative. And that would only happen for those 2 parts. So that will be the intervals in which that is the case for this problem. I'd say that's pretty nice. Okay, let's go to our last part D, and that will conclude the question number 4, and then we'll be going back to checking on these answers. Okay, question D, it says here the function g is defined by g of x is equal to f of x, all of this cubed. Okay, so if f of 3 is equal to negative 5 over 2, find the slope line tangent to the graph of g at x is equal to 3. Okay. Very good. So we have this all set up here so that we can now have a g function to look at. Okay. We want the slope line tangent to g. Right? Slope line. That means we need to know g prime of 3 to figure that out. But of course, g prime of 3 is going to imply that we need g prime of x first to understand that. Right? G prime of x, well, that's going to be all of f of x to the third power. And we take that derivative respect to x. Okay. So, looks like we got power rule to do it. So 3 times f of x to the second power. But cannot forget that this is a whole function that we took a derivative of. So we're going to need chain rule multiplied to that after the fact. So we have all of this as the result of the derivative of g for us. Okay. So if we're going to do g prime of 3, that's going to be the 3 times f squared of 3 and then f prime of 3. Okay, all shown right there. F prime of 3, that should be pretty simple for us to solve. That's exactly for us on the graph. 3 comma 4, it's very nice that we took that note earlier. So we can plug that guy in. But f of 3 now, that's going to be another thing to figure out next, right? F of 3 being the actual function itself. So at 3, we have it up there. Okay, but to actually find the original point, we're going to have to go back and do fundamental theorem of calculus one more time to figure out that exact point for us. So f of 3 for us is going to be the integral from 0 to 3 for the derivative function. Okay, in which the area from 0 to 3, thankfully because this area is now cut in half because we're going up to 3 there. Let me double check here. Yeah, I think we should be fine to assume that, even though it doesn't look like it. Oh, no, sorry, they gave that to us. Yeah, I had a feeling there. It would seem kind of wrong to just assume that. So, f of 3, they did give us to us early in the problem right there. Almost forgot about that, which to us is negative 5 over 2. Okay, so g prime of 3 then could be solved for here with everything plugged in. It's going to be 3 times negative 5 over 2, all that squared, and then multiplied by a 4. Got a little bit of work to do here, so it's going to be a 12 multiplied by 5 over 2, that's squared, 10 to positive, so 25 over 4. The 12 and 4 can simplify to a 3, so it turns to a 75. Quite large, but I think we should be still good for it off of this. Okay, so now that is the actual slope itself. Now we got to know the actual line, right? So it's y is equal to mx plus b. Again, in this case, m is the 75, and now we need to know that last bit for the y-intercept. Thankfully, they gave us the actual point. They did not give us the point. No, because they only care about the slope. So 75 being the slope, that's it. We actually don't need to know the full line equation. Okay. That was a little bit of a wild one, but we actually completed the entirety of problem number 4 all on a single piece of paper. So that looks pretty good. So we can go ahead and start checking this before we head off to our last segment together of problems 5 and 6. So let's go ahead and have a look here. So let's make sure that we are going to be switching to the right screen here. Okay. So going on to question number 3, I can go ahead and mark it up so we can just have it here for now as I mark up from my notebook here. So back to that whole coffee cup question, is that we have 1.3 or 1.6 ounces per minute that the coffee cup is holding. That's good. The approximation and the units, yep, both of them. So that's 2 for 2, correct on this. Okay. Next up, part B. is going to be a 2 differential conclusion using MVT. I did just that. Okay. And then, of course, we need to show that average rate of change of C of 4 minus C of 2 of 4 minus 2. I did exactly that as well. So that's 2 for 2 correct on this. Okay. Next of part C is that next we're going to have to go understanding that the midpoint sum is going to be exactly that, which I did exactly. So 1, 3, and 5. Again, I just used the distributive property to multiply the 2 at the end of it, but we're pretty good on that as well. And then the approximation itself ending at 60.6, that's good. And our last interpretation of is the average amount of coffee in the cup. That's exactly what I swapped to. So all 3 points are going straight to me. So part C is also correct, and we're 3 out of 3 for that. And then lastly, we have part D, in which we end up with B prime like that, 6.4 e to the negative 0.4 t. That's exactly what I have. And then B prime of 5, again, leaving it as just e to the 2, either denominator or negative 2. Both of them would work for this. And ounces per minute is the correct units. So I got both points on that. That's 2 for 2 correct on mine as well. Okay. Looks like we're doing pretty good. That is another 9 out of 9 for me. So I think we're doing pretty okay for the total amount of score that we got here. And then lastly, let's go to problem number 4. And let's see how this goes. So, x is equal to 6 is the only one, right? Okay. And they wanted us to consider f of 0, which, sure. Oh, no, that's the wrong one. Oh, no, sorry. Sorry, not f0. So, yeah, just only x equals 6. And then, no, that's only a 1 point. Okay, just notifying that that's the case. That's a 1 for 1 correct here on part A. Then for part B, this is a 3-pointer right here. So, yes, we needed them considering 0, 6, and 8. Those are all ones that we do need to consider. We end up with the calculations of negative 8 on 0, and then... Ooh, that's very... Did I do the wrong one? Negative 3. Thankfully, though, the actual absolute minimum is going to be... is negative 8 still. So I think I kind of lucked out on that one. I did kind of mess up the calculations. Let's look back on that one as well on that. But I don't think that's going to really be a main issue for this. Although it's f of what? Oh, I think that's why, because I messed up. Oh, shoot. Okay. I think I actually deserve a loss on that. Because 4 is a maximum, not a minimum. Okay, yeah. I'll take off a point for myself on that. But thankfully, still, the rest of it actually should be good. So 2 out of 3 for me on this. But we need to look back. Okay. And then part C is going to be the graph is concave down and increasing between 3 and 4 and 0 and 1. So 0, 1, 3, and 4. That's answer good. The explanation is good as well because we are doing concave down and increasing. I made the note on that. So we're going 2 for 2 on that. Okay. And then lastly, part D here is that we have the g prime function right here. Again, showing that chain rule is important for us to get 2 points on that. Wow, they really stuck it home for us on this one, so I'll do a double check mark on that part. And then lastly, getting a 75 on the slope, that is good. So that's 3 for 3 correct on that part. Okay, so before we go to the next problem, let's go ahead and take a look back as to what we dealt with earlier for this kind of a problem. So I'll keep my red here. Okay. So going back, this is problem B we have to look back on. F of 4 is not one of the proper candidates for the local minimum. Remember, we wanted an absolute minimum, meaning that we have to look for at a local minimum as some of the other candidates that we would need to look at. So 0 and 8 were indeed correct. Those were the right ones to do. But I chose 4, which is not good. 4 is not a local minimum. It is 6. It's a crossing from the negative to the positive side on the derivative that is going to be the main difference maker for the absolute minimums. So because of that, I should have done f of, so it should, let's see if I have space for another integral. So that's going to be f of 6, not f of 4. So we know what that equals to. So we're going to go from 0 to 6 of the f prime of x dx. Okay, so f of 6 minus f of 0 is equal to the area. So f of 6 is equal to that same area plus f of 0. Right? That's how we would have separated that out with a different point instead of f of 4. The area now is going to be a little bit different. So because we have the area of 2, the area of 6 altogether, 2 and 6, leading up to 4, and then we have the minus 3 as well. So let me see if we show that properly here. And for stopping at 6, all the areas adding up to is 2, 6, and the minus 3, with the area of the part that was underneath the axis there. Okay, so because of that, we're going to have the inside this is 2, 6, and a minus 3. And then with the f of 0, that is a minus 8 for f of 0 point itself being added. So this is going to be 8 minus 3 is 5. Minus of the 8 is going to be negative 3. So f of 6 was negative 3. I still lucked out with the right answer that f of 0 is equal to negative 8, and that indeed was the absolute minimum. It's just unfortunately I picked the wrong point for us, which was a silly mistake. We definitely should have known better on that one. But nonetheless though, with that all said and done, this is an 8 out of 9 problem. With a little bit of an oof from me, because that was a mistake that should have been easily avoided if we were reading and observing things properly on the paper. Okay, I think that really does conclude those two questions. So let's go onwards to the last section, and that really should conclude for us on this section here. Okay. So on the first page again, now we're gonna go with question number 5 here. Okay, we got this graph. Again, I'm gonna go ahead and move things over so that we can have everything written for us on the page itself. So with problem number 5, we have a graph here. It's gonna be a little bit different here. We have just a 4 marked there and a 2 marked there. And so this graph goes 1 up above and then 1 down below. It actually goes underneath for a little bit like that. That's the section of R. So we have f of x is equal to 2x squared minus 6x plus 4, and g of x is equal to 4 times the cosine of 1 over 4 pi times x. Okay, so and then R is bound by f and g. Okay, so we gotta now find the area of R. Now, how in the world are we gonna do that? Right, area between two curves. Oh my goodness, this one's a real whack one. But I think either for any of the students that will look at this at a later time, is that at a certain point we should be having the experience to know how to do this kind of question, right? All we need to know is that we need to know, again, it's basically the integral of the top function minus the bottom function, right? And that will cut out all of the bottom area because we're subtracting away from the, we're cutting away the bottom part that we don't want anymore, and we're just left with the area between the two. And of course, any other area that's underneath the curve, right? Because the top part will see it as a negative function, right? Or the top part actually wouldn't see it at all as part of the function, but the bottom part will see it as part of the negative function because it does go underneath. We are already subtracting it, so it actually will cancel out and go to a positive state, which is pretty nice for us, I would say, for ourselves. Okay, but now we're still with the same issue. What in the world is the bottom function or the top function for this kind of graph? Well, there's a couple of clues that we can look into it ourselves, or there's just a couple of things that we can figure out as well. But clue-wise, g of x is a cosine function, right? There is, other than just that 4 coefficient, hello, camera? You mind? Okay. Yeah. So the g is a cosine function, which no other massive coefficient is just a single positive 4, and there's no real big shift. It's a quarter of a pi x. It looks like cosine because cosine has the form that starts on the top and it goes underneath like that. It seems like that should be the top function, but we can hold off on that for a second. Secondly though, f is a 2x squared, right? Even though it's a minus 6x Dude, camera, come on. You're literally looking at the same page for the whole time. Is this really just too far for you? Refocus on? Man. Okay. So, for this, alright, because it's the 2x squared minus 6x plus 4, this is a concave up all the time. Right? At least for everything that's going to be related to this function, right? Okay, with a concave up like this, the only real one that can fit that shape is going to be known as the bottom function for us. Okay, and this guy dipping underneath the x-axis, it seems like a pretty good deal for us because the minus 6x will do that for us as we approach the vertex of this parabola. Alright, this is getting really annoying. Dude, like, you were in focus. Why must you just leave focus all the time? Is there something that's going on here that I don't know about? Like, do I need to bring this camera closer? Man, I really thought this will work a lot better than it would. But investing in a better camera will be in the cards in the future if this live stream comes out to anything that's worth anything. But for now, let's just focus still on the problem. In any case, though, we can actually go and solve for this even if we got it wrong, because we just got to swap the top and the bottom instead if it turns out we just get a huge negative answer, because this definitely should be a positive area we're dealing with and not a negative one. So let's call it as it is. So 4 cosine 1 over 4 pi times x minus all of 2x squared minus 6x plus 4 in the dx. This is going to be our top minus bottom relationship for this kind of graph. So let's have a look here. Okay, for one, let's clean this up a little bit. That this is 4 times cosine of 1/4 pi x, and then minus 2x squared plus 6x minus 4 dx. Okay, so that is a cleaned up version of that we can take a much easier time on the integral on this guy. So let's have a look here. 4 times cosine of 1/4 pi x. Well, that will turn this into a negative 4 sine of 1/4 pi x. The next issue, though, is that we're going to have a problem with the coefficients if we took a derivative back on it. So in order to fix that coefficient, we need a 4 over pi that will indeed match up with the coefficient. And what am I talking about? It's a sine. It will go back to positive cosine, so that's going to be positive still. So positive 4 sine of 1/4 pi x, and the coefficient canceller of 4 over pi looks like it's pretty good for us on that regard. Next up, we're going to have the negative 2x squared. That's going to be negative x cubed, but that's 2 over 3 instead to cancel out with that. And then 6x will give us 3x squared as the next step of the integral of a positive 6x. And the minus 4 is minus 4x and then plus c. Okay. Now, we don't actually supposed to have plus c. I almost forgot as well. That we're only really going from 0 to 2. They did tell us where those two guys intersect as for the full area of R. So our limits actually for the integral are from 0 to 2. Let's swap that to an actual form of going to be evaluating limits for this kind of integral. Okay. So our first part of this evaluation is 4 times sine of 1/4 pi times x, which is 2. And then 4 over pi is a coefficient, minus 2/3 of 2 to the third power plus 3, 2 to the second power minus 4 of 2. Okay, and then we're going to subtract that with now the second part of this, now with the zeros. So it's 4 times sine of 0, because that all cancels out, 4 over pi, and then we subtract that still with 2/3, 0 to the third plus 3, 0 to the second, minus 4 of 0. Okay, now thank goodness though that the second part of the 0 all in itself just gives us exactly 0. How convenient. But we still have to evaluate the rest of the top part of the function. So that's going to be given to us instead of, so it's going to be 4 times sine. And if we simplify this part, that line right there becomes pi over 2 times 4 over pi minus 2/3 of 2 to the third power, which is 8, plus 3, 2 to the second, which is 4, and then minus 8 again there. Okay, so sine of pi over 2 thankfully goes to a 1. So that's 16 over pi minus, so 3 times 4 gives us 12. So 2/3 of 8 would be minus a 16 over 3. And then 12 minus 8 is a positive 4. Okay, so positive 4 being added to all of that will give us our final part here, 16 of pi. And then we're going to subtract the 12 over 3, which is going to be 4 over 3. Okay. A little bit of a long-winded one for something that is not a calculator problem, but it just takes a few steps for us to go through to make sure that we're on the right track for this. Okay. And because 16 over pi and 4 over 3, 16 over pi is going to be larger, we're in a positive area, so it looks like we did the proper subtracting the way that we should have. Okay. So part B is going to be right, but do not calculate an integral expression that gives the volume of the solid generated when R is rotated along the horizontal line, y is equal to 4. Alright, now this one's going to be maybe a problem for a lot of students because this truly is kind of the ending part for AP Calculus AB, is going to be the rotations around a line or around an axis. They really aren't pulling their punches here because this is going to be part from the line. So why don't I go ahead and change my color here on my pen for just a second so we can all see it. Is that they said that the line is y is equal to 4. Remember that's going to be the important part, right? We're going to rotate around that. So that's a horizontal line at a y equals a number. So if we go and take that, there you go. That will be the line at which we get this entire R area and we start swinging it around and then we form up a volume. A very interesting cone-looking shape thing, I'm sure, if we did take the time to put that all together. But in any case, though, we have all of that going through. So let's have a look to see what that will look like for us. Okay, but now remember, though, is that this is actually going to change a lot of things because the area that we're looking to calculate and turn into a volume is right here, right? But the issue now, of course, is that this is going to change how we measure it because we're measuring from y is equal to 4. Okay? So now we can actually have a different top and bottom because we have to measure from here to here as well as here to here, right? So here we have another different bottom there, and here we have another top there. Again, one will have more area together than the other, and one will be subtracted from the other in terms of function, right? So if you want to bring back the generalized form of looking for these types of problems here for the swinging around of an area across a certain line, the most generalized form is that it's going to be the integral of, at least the way that I like to call it, right, is that it is the line minus the big R, the big radius, all that squared minus the small line minus the small r, oh, that's still a big line, all that squared, d, and in this case, right, it's going to be dx because we're measuring it vertically, as we've shown with our arrows. Again, think of it as a pi r squared integral, right? So the pi is just one of these guys just kicked off to the side. We'll deal with that later as a coefficient, but again, it's pi r squared like that to turn it to from an area, right? Pi r squared is an area, but we took the integral, making it a full volume. Okay. So this guy needs to be substituted as such. Okay, we're still going from 0 to 2 for this problem, right? Because that's how we're going to go across the x-axis like that. But then we got a lot to fill in for, right? The top part, right, that we're going to measure here is that it's the 4, okay, right? And then if we subtract it by the big R, right, the big radius that we're moving it by. Actually, let me think about this, because we're actually rotating this around the top part. we actually do want to subtract the lesser part here. Let me double check here, because 4 is the maximum we can really get to from there. And then if r gets closer to 4, oh, closer to 0, that's closer to 0, that's right. Okay, no, we're fine. I think we're all good to go here. So the length is 4 minus big R, which is going to be that lower bend of the graph, which that already should be f of x. So let's put that in there. So all of 2x squared minus 6x plus 4, and then all of this squared minus the line again, 4 minus, now the small r is the 4 times cosine of pi 1/4 pi x, all that squared. Okay, so this is kind of smushed a little bit, so let's go and do a little bit of simplification while cleaning this all up. So that's still pi on the outside, 0 to 2, of 4 minus, now minus 2x squared plus 6x minus 4 all squared, and then minus the 4 minus 4 times cosine of 1/4 pi x, all that squared dx. Okay, we can do one very little simple bit of cancellation right there, and we will no longer be calculating anything because they told us not to. So we just have it set up here, which is just about ready for the calculator if we were to do something like that. 1/4 pi x, all of this squared. And this will be the result of finding that volume when it is rotated about the y=4 line. Okay, so I think that's pretty good. We'll see what the answer looks like, if what I had was from good memory or not. But our last part here is part C, which is the ending part for this problem here, for part 5. So it says here the region R is the base of a solid. Okay, so for this solid, that's how I write solid. For this solid, each cross section perpendicular to the x-axis is a square. Okay, so same idea here is that we're going to write, but do not evaluate an integral expression for the volume of the solid. Alright, there you go. Another doozy of a problem for people who might not be very good with the whole areas and volumes businesses with integrals. But in a sense though, this is actually one of the easiest ones because it's a square. So what we're trying to imagine here is that we only wish to take this, right? That is the base of the square. Again, you're imagining it being raised up as a square as each of them go up vertically, right? So if that's the base of the square, we still need to find the height of the square in order for us to start understanding volume, right? Because if we take the area of one square and then we integrate, we are adding up all those areas going all the way down as per what integration really is, which then gives us a total volume. But a square? A base? Well, if only we knew from the very, very classic geometry property that for a square, the base and the height are exactly the same, right? So for us, the most generic sense of this is that the integral of that base squared dx, because we're still going vertical side on this, well, that's going to be the volume. Okay? So that's pretty nice to keep up with. But now, of course, we need to then follow up with what that actually looks like for us for a proper base for this type of problem. Well, if only we hadn't done that earlier. This whole part of part A, we did do exactly just finding the difference between for just that area R. Again, not across any different line, but just for each of the different heights between the top and bottom of that. Oh, I'm sure we can get to something good real soon here, is that we should be able to have the base known as, right? So our base here is going to be that, in our case, f, because f is the bottom part, so the top part would be g of x minus f of x. Okay? So, because of that, we should now be able to determine what's going to happen here. So, our integral here is when g of x minus f of x would be 4 times the cosine of 1/4 pi x. Okay? And subtracting it by f of x, which is going to be 2x squared minus 6x plus 4. Okay? And this integral will be evaluated from 0 to 2. But also, the entirety of that base, that subtraction, is that one side of the square. The other side is just going to be squared. So it's multiplied one into the other dimension. And then we just add it up all the way down through the integral, which is why we have it from 0 to 2. And of dx will then give us the total volume based on square cross sections for that shape of those two functions. All right. I think that was pretty satisfactory for what we've done so far. A little bit of an extra dive into maybe some parts that students right now are not getting to, but will definitely be fair game on the exam. So who knows if that will show up for this year's exam if we continue to the end here. Okay, so lastly here we do have part 6, which also includes the end of the exam. So I'll finish up this part, which only looks like only parts A and B, but we'll go through this together and then we'll grade parts 5 and 6, and then we can get our total score at the end of all that shortly afterwards. How exciting. And that really would conclude the end of our stream at that point, unless of course anyone had any other questions that we can follow up on to keep this going. But for now, let's go ahead and get to problem number 6, and let's see what happens here. So context-wise though, we have a differential equation, dy over dx, which is equal to e raised to the y power of 3x squared minus 6x. And so it says here, let y be equal to f of x for the particular solution, and that passes through 1, 0. Okay. So that's all the context that they really will give us for question number 6. So let's start with question A here. So write an equation for the line tangent to the graph of f at the point 1, 0. Use the tangent line to approximate f of 1.2. Okay, there you go. Looks like we've got quite a few things that will help us out here. Hopefully on this section. Let me just make sure I get this all set up properly. Okay, very good. So we have now this part here in which they want us to make a line tangent graph here. So let's see here. All right, we have the point 1, 0, and then we're going to do an approximation after the fact. Right? Okay. So in order to find the tangent line, we need to know the actual slope of that line, right? The slope, of course, is going to be the dy over dx, and then we're going to plug in the 1, 0 into it because we have both y and x values in this guy, right? Again, it's e raised to the y power, which in the case would be 0, of 3x, which is 1 squared minus 6 times a 1. Okay, pretty good. Thank goodness that e to the 0 is just a 1. We still don't have calculators allowed in this section, so that's pretty good. And so we have the rest of it as 3 times 1, so 3 minus a 6, which is a -3. That will be the slope of the tangent line. Okay, now we're going to need, again, the actual line itself is equals y equals mx plus b, so we need to know that b part. Okay, thankfully though, we already do have that point 1, 0, so we can plug everything here. So 0 for the y, m is -3, the x was 1 there, and then plus b. So we have 0 is equal to -3 plus b. Pretty self-explanatory that b should be a +3. So our tangent line equation that results from all of this is going to be a y is equal to -3x plus 3. Okay, pretty good. So they want us to find that. So that's the first part in which we can keep track of. That's the first part of the answer for part A. But also now we want to do an approximation of f of 1.2. Okay, so approximation for that is the y is equal to the negative 3 of 1.2 on the y, on the x that is, sorry, plus 3, which is negative 3.6 plus 3. So y is equal to a negative 0.6 as a result, right? So that's going to be the next part. That is the approximation of what they asked us to do. Okay, not too bad for this first part. Now it's part B already, the last part for part 6, but let's have a look at what this looks like. So it says here, it's just to find y is equal to f of x, the particular solution to the differential equation. That passes through (1, 0). All right. Well, we've got ourselves out with our work cut out for us because it's dy over dx is equal to e raised to the y power of 3x squared minus 6x. Okay, so this guy here has a little bit of a back and forth here because we have both y's and x's in the differential equation, which means that our big word here for the day is that it's called the separation of variables. Okay, that is a method at which we can separate all the y's and all things related to that to one side of the equation, and all the x's and those guys related to the other part. Okay, so that is very important to us because that will then show us that we do understand that we can do dy over e to the y. We can divide that to both sides. Okay, and we can multiply dx to both sides to keep it so that the operation of integration can be done on either side, as we can then integrate either side of the equation as such with each of the variables to each of them. So that's exactly what we're going to do. We're going to integrate on both sides, and we should be able to then determine what we're looking at once we get across that. So dy over e to the y. Okay, thankfully that was just, if you can rewrite that just for our own sakes here, that it's e to the negative y dy, and then the 3x squared minus 6x dx. So this integration is pretty simple. It's going to result in negative e to the negative y, keeping track of the chain rule that will result from that, plus c is equal to x cubed minus 3x squared plus c. Okay, now we could just subtract the plus c's because the only plus c's need to be on one side of the equation. So negative e to the negative y is equal to x cubed minus 3x squared plus c. And now though, we need to remove the negative y from that exponent spot because we want it back down with the rest of them. Okay, but first off, that negative coefficient is going to be hindering to us. So let's go slap that negative 1 over to the other side. So then we have e to the negative y is equal to negative x cubed plus 3x squared plus c. Again, c's being negative doesn't matter. It's going to be whatever it is if we ever get it to swapping it over to the other side of the equation. And so with that, we really are looking for to make sure that we can separate out the negative y. So the natural log then on both sides will help us remove that y from the exponent spot. And so we have to do that for both sides. So thankfully, because of us being so studious and knowing exactly what natural log does in the face of e raised to a variable, we can shove that negative y away from the exponent spot and into a coefficient spot. So that's negative y of the natural log of e is equal to the natural log of everything of negative x cubed plus 3x squared plus c. Okay, pretty nice, right? But then, of course, is that we need to do our last bits here. The natural log of e just goes to 1, okay? And then the negatives needs to be swapped back again. So positive y is equal to the negative natural log of negative x cubed plus 3x squared plus c. And then, lastly though, because we don't really like the plus c inside of a natural log because we want plus c to be solved on its own from the outside spot, what we can do is that we can take advantage of our natural log rules to understand that by saying plus c on that side, we are really just saying a multiplied by c as a coefficient. Well, if we're going to really be as accurate about it, it's a natural log of c that's multiplied, but then natural log of c is to be just another constant that we will solve for at a later time. So to really clean everything up, it's y is equal to negative c times the natural log of everything else, negative x cubed plus 3x squared. Now this is going to be the actual equation here, but we're still not done yet. Why? Because we want to find, we actually told us that they gave us a point here for the particular solution that passes through. So now it's time for us to plug everything in. So y ends up as 0 is equal to negative c times the natural log of negative 1 to the third power plus 3 times a 1. Okay, so negative c is equal to, let me double check if I got all this right, because this seems like we're falling into a trap here. But in any case though, I think we should be pretty okay. Yeah. Okay. So it has a natural log of so it'll be negative 1 plus a 3, and then c times the natural log of positive 2. Okay. Let me think about this for a second, because I think we kind of walked into something that we should not have. Let me have a look here. Yeah, okay. I think I might have been jumping the gun a little bit too much with this part here. Because if you natural log both sides, then it needs to be a 1 in there. So why don't we take a couple of steps back here, and let's not remove the c out like we did earlier. And let's just start it off again from here, because yeah, I'm walking into a trap where c is 0, but that's not really going to help us out over here. So let's try this again. So 0, plugging in from that previous spot, a negative natural log of negative x to the third plus 3x squared plus c. And again, we need 1's there now. So 1 to the third and then 1 squared. Okay, so negative natural log of negative 1 plus 3 plus c. And then because of that, we have the negative natural log of positive 2 plus c. Okay. Now, thankfully, though, because now the negative natural log is going to 0, the only way of doing that is making sure that the natural is going to be 1 inside of the natural log, thanks to our previous rules of understanding how logarithms work. So 2 minus 1, again, that's got to be c, so that the negative natural log of 1, which is going to be equal to 0. Okay, so now we have it. So it's going to be y is equal to the negative natural log of negative x cubed plus 3x squared minus 1. And there you have it. Okay. We've got our final solution here. Final answer, that is, for this kind of a problem. Okay, a little bit of a challenging one, I'd say, at the end there, because some steps that I might have forgotten. But I think we're all the better for it, just to see now. We can go back to see what the answers are. So let me get this set up here so we can take a look at the monitor here. Let's see, I just received a bit of... Okay. And let's make sure, let's go back to problem number 5. And let's go over this together now, shall we? So problem number 5 here, we have the area now is 16 over pi minus 4 over 3. That is indeed correct on my part, so that's good. Let's see, and so the integrand, so right there, so the 0 to 2 for g minus f, that's exactly what I wrote down. So we'll do that for that part. And then the antiderivative itself, yeah, running through the whole derivative, yep, so both parts I got through. So 16 over pi minus 4/3, that's all good. That's 4 points out of 4, that is correct for me. Very good. Okay, part B is going to have this volume there, which is going to be pi on the outside, 0 to 2, and then the 4 minus all of f first, and then all of that squared after the fact. That's very important to note. Okay, they could have done the simplification, but I guess they didn't really want to care. And then it's going to be the 4 minus all of g instead of all that squared on the outside. So yes, we're good on the limits and constants, and the integrand itself, no, 2 points for me. So that's 3 out of 3 correct there as well. Very good. Okay, and then lastly, for part C on this, we have the volume given as the 0 to 2g minus f all that squared. Okay, and g minus f all that squared is exactly what I have there, and then we just leave it like that. Good. So both parts are good here. So that's 2 out of 2 correct, and that's 9 out of 9 on this page. So that's nice. Okay. And then lastly, let's go to problem 6. This one's a little bit of a doozy, but I think we should be fine here. Negative 0.6 is good as the approximation. dy over dx at 0 of 1 comma 0. Yeah, plugging that in. Yep. Oh yeah, I should remember. I should keep that in mind as to how they show how you're gonna plug that in. Okay, something for me to remind myself next time. Tangent line equation of negative 3, making it positive in the y-intercept. Again, yeah, that's still a correct form for us to do. So that all matches those. So that's 3 out of 3 correct for me as well. Okay, then part B, which is the massive part, which is going to be the main thing here. Okay, if you forgot the plus C, oh, I made jokes about this all the time in my videos, but if you forgot the plus C, they will tell you that you are going to get only half points. Man, I wish that they made it so you get 0 points. But nonetheless, though, can't do it. But I mean, well, no separation rules, you get 0 points. That's obviously well deserved. I think everything there is well deserved for what we have already so far. Okay. So let's get back on the focus here. So one, the separation of variables, which we have, right? The dy going to the dx. Yep, I definitely have that. Swapping that over, so that's good. Okay, then the antiderivative itself, yep, deriving both sides, 2 checks for me on that one. The constant integration, of course, I made sure I have that. Uses initial conditions, so plugging in the 1 comma 0. We definitely spent the whole time doing that. I had to correct myself in the middle of that, but we still got it through nonetheless. And then the natural log is the -1 on the c, so c is equal to a positive 1 that way. Sure, at least for me, that came into a -1 at the end because it shows in this form at the end, which I saved it to the very end to do that for. So that's still good. And then solving for y, with y being equal to all of that, that's exactly what we need to have. Negative x cubed, 3x squared, and then a -1 with a -1 on the outside of the natural log. That is all very true. So count them up. I got exactly all 6 out of 6 points for this problem. That is correct. So that's a 9 out of 9 on this page as well. Okay, so let's go back here and let's make sure we count up exactly all that we have. So once again, just to go, if you really want to go really quickly over part B, because that's the one that was the really longest point. Again, this is all incorrect for me that I caught myself before we finished it off, that the c constant needs to be solved for inside of the natural log. That makes our lives much easier to solve for that c. Later shows up in this exact equation. That should have been it. Remember, the big part they did want you to do here is the separation of variables and then doing the integration. That actually by itself is literally half of the problem here. Right? You get 3 out of 6 points if you did just up to here, of just being able to separate out where the y's need to go and the dx needs to go to the other side. So that way you can set up for doing the integral, which then will give you 3 out of 6 of those points. The remainder, of course, is going to be doing the work, making sure you have the right plus c that you will solve for, and then you just clean it all up into one nice equation, in which is what they're looking for to give you those final points. Okay, so that's 9, doing that problem number 5. Then going back to problem number 5, yep. So we had this, again, we had all these different volume problems. Okay, so the area itself, again, that was exactly it. Top radius minus bottom radius. Then doing the actual work for it will give us the 16 over pi minus 4/3. Again, got that one correct. setting up for the one of the line. This is, I would say, one of the hardest ones for this entire packet, but being able to keep track that it's r squared for both of them, it looks like you didn't really have to do the simplification of that with the 4 and the -4, but no harm, no foul. That's not really anything that they should care about when they're grading you. But in any case, though, that is how they would have graded that, at least to the part where you need to make sure you're doing the right way of doing the 4, that line, again, the y equals 4 line, and then subtract away the radius from the top to the bottom and squaring each of those radii afterwards, and then doing the integral. Again, all that order is very specific for how to get that exact shape that they're making the revolution out of. So, keep that in mind. We got everything else good here as well. The square was the easier one because it's just the subtraction and squaring it. It's a square, so that's all you really need to keep that in mind for. 9 points, so we're at 18 so far. Then it's problem number 4, in which I got dinked off 1 point because I got lucky though, but I did make one mistake on that part. But first, of course, we were talking about local minimums, and so there's only 1 point in which that happened. There's a single point for that, but a very easy one. Then, of course, I got mistaken at choosing the wrong points as a candidate. I got 2 out of 3 of them correct, and I did choose the right one, which was actually the correct result of the absolute minimum. But, of course, being able to discover which candidates those would be and then finding out for each of them is very important. Then it's going to be the question about the speed increase, or not speed increase. They just specifically told you that it's going to be concave down and increasing. Again, both of which will have their own number line analysis for you to then describe the exact different sections in which this will be the true case. And then lastly, it's going to be the actual function itself, with them giving us some sort of new equation, and then we need to find that slope. Pretty simple. Just remember that we are dealing with chain rule here because we have another function that's being derived, not just x. Okay. Next order of business that we're going back to is question number 3, where we had that whole coffee cup business of this entire line of the table there. And so again, they wanted to do things like finding an approximation, which will need an average yet a change, which we calculated for. And then next we want to use MVT, the mean value theorem, which is very important for us to memorize as students in AP Calculus, such that you should be able to then figure out where the actual guaranteed value of one of the derivatives would be, even though we actually don't have the function in hand. Even with just a few pointers and a table, we can still use MVT to describe that we can guarantee one derivative value which they're looking for. Okay. Then we have a midpoint calculation. Oh, those only worth 3 points. I really hope they'll be worth more. But because of that, we did midpoint evaluation, which is just from strict memory about knowing how to do that, at least in terms of finding each different height and then multiplying across the bases. But then the big kicker, though, is that how we were able to find that this is representing the average value of the function itself by dividing by the limit of the definite integral. And so we were able to decipher that, let them know. We get 3 points for that one. Okay. Then part D, we're dealing with another derivative function here, in which we just need to go make sure we do that properly. It really was as straightforward as it could have been. 9 points for me. That would total me from 27 from the past, 28, and then on 4 I got dinked 1, so 18, 26, adding another 9 makes it 35 versus the 36 I would have maximum. Okay. Then part 2. The problem number 2, back to some calculated problems here, is that they wanted us to find some values in which that the speed is 2. So that means we have to evaluate that v is positive 2 and negative 2. Again, those two are valid values for the velocity function for us to then find on the graph, because we graphed it ourselves on the calculator. And so with that, we just followed along with the prompt to make sure we're in the right range of times. We found those two. We got 2 points for that one. Okay. And then next they want the explanation as to why we can get the integral to show that we can get a specific position at 5. Okay? And so because of that, we just had to take the integral of velocity using good old fundamental theorem of calculus to understand that we get certain points of position out of it. Because we knew one already, we can then solve for the other one. Pretty straightforward. 2 points on that. Okay. Then we want to find all the times in which the particle changes direction. That, of course, is just a simple terms basis knowledge here, that of course if you cross the x-axis on the velocity graph, then that means you change in direction. So we found the 2, and then we count them, of course, 2 times at the exact points. Okay. The speed of the particle is increasing or decreasing at time equals 4. Remember, speed means that we have to then evaluate that it's velocity and acceleration. So remember, if they're same sign, so both acceleration and the velocity are both on the same side, so same positives or same negative, good enough for it to conclude that it's speeding up. While on the other hand, if one is positive, like velocity is positive, and then acceleration is negative, that will then determine that it is slowing down. So because of that, we then found for both velocity and acceleration that they were both indeed negative from our work, so we can conclude that we are speeding up at that time that they asked us for. Okay. At the very end here, we have problem number 1, which we were dealing with a specific gravel plant, I suppose, in which we had a rate at which gravel was entering into the facility. They told us a steady rate at which the gravel was being used up, and then the starting amount of gravel. So quite a lot of things going on there. So we want to find g prime of 5. That's the most straightforward one. We just do some simple derivation by hand, and then we just plug in, and we should be able to get a specific change. Actually, this one I did... Oh, I did by hand. Yeah, I did by hand. And then we just plugged it straight away through. And so that way it's going to be the change in the rate, because g already is a rate function. So g prime of t is a change in that rate function for the amount of gravel that was added into the facility. Then the total amount that was going to be at the entire time that the that arrives into the facility. So it doesn't care about how much it started with, it's just the amount that the trucks keep bringing into the plant. So that's a simple definite integral from the rate function, and so we just get a specific answer. 2 points for that one. And then part C is going to be now the actual amount. Again, is it decreasing or increasing at a specific time? So that's going to be comparison of both the g function, because function g is how much is the rate at which the gravel is being added into the plant, and while the 100 was the flat rate in which the gravel is being used up at the plant. So with the comparison with the negative result from g minus the 100, that means that there was more gravel being taken out of the plant at that time, because they're not adding the same amount of gravel back in. Okay, and then lastly, part D is going to be the amount at the end of the day that is still left over. Okay. So, it's the maximum amount of unprocessed gravel at the very end. Okay, so that's a maximum function. So that means we need to go then figure out something based on the graph of what we have here for some possible maximums at the start or end, or at the derivative, right? That crossed the x-axis from the positive side down to the negatives. Oh, excuse me. Sorry, I couldn't mute my mic fast enough. But in any case, though, we have this this function out here in which we're testing to see where the maximums will be like, and then we just do the calculations accordingly, and it turns out with that right amount that there is a total maximum of about the 635 tons of gravel left. Okay, so because of that, my total came out to be, from out of 6 problems, each of them out of 9 points, my total score, if I can spell properly, my total score is out of 54, because it's 9 times 6, 54 points total. I got 53 out of 54. So not too bad at all. That's definitely within the range for a 5 if it's only in terms of just the free response questions. So again, this is just going to show that this is the practice that is needed for people to really start getting on the pace of getting the types of results that they're looking for on this kind of exam. So in any case, though, because I am doing this on, again, this free response packet is an old one. Again, to reiterate, this is the 2013 one. The College Board always puts up their old test questions up on their website, and because of that, this section is actually only, right, so 30 minutes for 2 problems for the calculator part, and then on the other side it's 1 hour for the other. So this hour 30. The entire test, both free response and multiple choice, is a 3-hour test. So then you have another hour 30 for the multiple choice as well. So in any case though, I take just about 3 hours to do the full explanation through and through for the full packet. But again, for those that are testing on their own or going to take the test in a few months, you should be practicing on both free response and multiple choice on your own, and indeed timing yourself, because time on the test is important. I'm not really in any rush state doing this, so maybe that might contribute to getting the problems done a little bit better. But the practice is still going to be up forward and just about the same for all the students, to make sure they make sure they eliminate all of their silly mistakes and understanding how to solve the problems usually when you first take a look at it. Okay. But I think other than that, because there's no other real updates from anyone else viewing right now, that this will conclude the stream, and this will be it for now. I'll be back again most likely on Tuesday to do another packet, unless we start getting more requests for actual individual problems. And so with that, I believe that should be just about a wrap for today. We'll definitely look forward to seeing all of you on Tuesday again, once we can get to another part of this. So we all thank you for watching, and we'll see you all soon. I'll be doing one more video tomorrow and a few more shorts, and we'll see you next time as well.